Hello everyone. Today we are going to explain what an ARP table is, what a MAC address table is, and what a routing table is, HCIE. These three tables can be said to be very important in data forwarding. First of all, if in the future PC1 wants to access any device, this process is actually similar to sending a package. Isn't it true that if I want to deliver the data accurately to the other party's hands, then I definitely need to have the recipient's name, address, and phone number, as well as my own sender's address, sender's information, and sender's phone number. Only with this information can I accurately deliver the package to the recipient's hands. When we transmit data, it's actually the same. However, in this context, we need to consider several parameters. First, we need to consider the IP address of the person or device sending the data, as well as the IP address of the recipient. Additionally, during this process, we need to pay attention to the fact that the destination IP in the SIP is actually just a global locator. It's similar to a person's name, but if you want to send something directly to them, you need to know at least which city or country they are in. Otherwise, finding someone globally would be very difficult, meaning you need to pinpoint their exact location. Now, in this process, we need to incorporate another parameter. It's called the source MAC address and the destination MAC address. Now, if we talk about IP addresses in this process, they provide global positioning, meaning I can see your location from a global perspective. Meanwhile, the source and destination MAC addresses allow me to see your position on a specific link. All devices connected through our switch are on the same link. So, in this process, my switch G is connected to these two computers on the left. And it's also connected to this router, so we are actually connected on the same link through the switch, which is called a local area network, LAN. Over here is also a LAN, and they are two different network segments, two LANs. Now, if we look at this process step by step, suppose my PC1 wants to access PC2. At this point, if it wants to access and generally before accessing, if we want to test whether communication is possible, to test the connectivity, we use a command in our network called ping. For example, when making a phone call, we always start by saying, "Hello, can you hear me?" If the other person says, "Yes, I can hear you," then we proceed to discuss other matters. Similarly, in the network, if I want to send some data, I first need to ensure that our connectivity is fine. I would choose to ping the other party's IP address to test this. For instance, if my PC wants to access PC2, I would use 192.1168.1.2. In this process, if I want to send the data out, I need to specify who I am sending it to. The packet must include the source IP, destination IP, source MAC, and destination IP. Here, the source IP is our 192.168.1.1, which is my own. And what about the destination IP? I want to send it to 192.168.1.2. So what about the source MAC? The source MAC is simple. We can directly query it from the device. It is provided by the manufacturer and embedded in the chip, so we don't need to configure it. However, there is an issue with the destination MAC. Here I know the other party's IP because I need to append the other party's IP after the ping, but do I also append the other party's MAC? No, I don't. So here I don't know what the other party's MAC address is. What should I do? At this point, I know the other party's IP, but I don't know their MAC. So I will send a request. Send an ARP request packet and I will ask, what is your MAC address? At this point, the PCE will send out an ARP request packet, which is a broadcast packet. As long as the switch receives this broadcast packet, it will send a copy from all its remaining interfaces. Now, during this process, my AR1 can receive it and PCR can also receive it. As a network device, will R1 also broadcast it? No. Each interface of the router isolates the broadcast domain, meaning when it reaches me, I will check it. Are you looking for me? If you are indeed looking for me, then I will reply to you. If you're not here to see me, then I won't bother and I won't help you forward. So at this point, will I respond to him? No, he won't. For example, if someone in your class is asking, "Who is the excuse? What's your phone number?" and you're not the excuse, would you respond to him? You wouldn't, because he's not looking for you. Only the excuse would respond and say, "I'll tell you. What is my own phone number?" Now, in this process, the PCE is asking outwardly, who is 192.168.1.2? What is your MAC address? And only our PCL will respond to it, because it is 192.168.1.2. After responding during this process, the switch helps forward it to the PCE to assist you in telling PC1. What is its MAC address? Now, in this context, let's say our PCR responds. It tells PC1 what its own MAC address is, so that in the future, when PC1 forwards again, it will know. Originally, your destination MAC, for example, during this process, we copy it down as 0EA6. Then at this point, I can communicate. Now, in this context, my PC1 can communicate with 192.168.0.2 during this process. Let's see if I can receive a reply from PCR. Okay, at this point, if we are communicating within the same network segment, I want to ask everyone during this process, does the switch know whether I will exit through port 2 or port 1 in the future? Does it know here? Does it know? Actually, during this process, first of all, I want to tell everyone that it actually knows. Why? Because in its own table, it will generate something called a MAC address table. How do you view it? It's called display MAC address. During this process, it records which interface corresponds to which MAC address. So if in the future, when I look for this PC2 again, during this process, when I send data outward from my interface, as long as this switch receives data from others through my own interface, for my own interface, I will record the data I receive. For example, if someone sends me data, I will note down their MAC address, say 79D2, and I will record which interface received which MAC address. Therefore, here the MAC address indicates the MAC address that is placed. And us interface its corresponding relationship. Now, during this process, I have learned in the future, I will forward based on this MAC address table. If my MAC address table does not have the destination MAC it is looking for, what should I do then? I will send a copy from all my remaining interfaces, trying my best to help find it. If it cannot be found, then there's nothing more that can be done. If in this scenario, like earlier when I sent an ARP broadcast with my PCE, then our switch does not check the table, it directly floods. In other words, it sends a copy from all my remaining interfaces. At this point, the switch actually completes communication based on our MAC address table. Now, if I may ask, in this scenario, does PC1 send an ARP broadcast every time it wants to find PC2? If so, the overall efficiency would be too low, right? So in this case, it will store it in an internal table called the ARP cache table. We can check it using ARPA, but during this process, I found it was empty. Why? Because in the ENSP simulator, the aging time of the PC ARP cache table is particularly fast, averaging about 2 to 3 minutes. If you want to see it in the future, you can have them communicate again. At this point, if we check ARPA again, it will be in the cache table. In the future, before forwarding, I will check my cache table to see if your address is there. If it is, then according to my table, I will encapsulate the destination MAC and send it to you. If it's not in my table, then I will need to send an ARP request packet to inquire. What is your MAC address? This is how we communicate within the same network segment. So if during this process, let's say I want to find my PC1, who should I look for? I should look for this PC3. At this point, our data is transmitted like this. May I ask, is the destination MAC I fill in at this time also the MAC address of PC3? Everyone can think about it. If I want to access 192.168.2.1, then at this time my source IP is 1.1 and the destination IP is 2.1. But what about my source MAC and destination MAC here? The source MAC, we say, is relatively simple. It's just my own MAC. But what about the destination MAC? Is it also the other party's MAC? Let's see, if I want to know the address of PC3 here, and I directly ask, I send an ARP request packet to the switch. Will the switch help us broadcast it? But can it find a device called 2.1 among the devices connected within its area? It cannot find it. And the router here will not help you forward this broadcast packet because the router's interface isolates the broadcast domain. The interface where the router is located is a broadcast domain. This part is a broadcast domain, and this part is a broadcast domain. So it will not help you forward it. So what do we do at this point? Here, the switch can help you find our R1, allowing R1 to assist you in communicating between different network segments. At this point, our PCE encapsulates the destination MAC, which is no longer the MAC address of our PC3, but rather the MAC address of our gateway, specifically the 0.254 of R1, meaning the MAC address of this interface on the left. So during this process, the destination MAC we fill in here is the MAC address of this 000 interface. The switch in this process forwards based on its own MAC address, knowing that through this interface it sends to R1. Once R1 receives it, it first needs to check its own table, which is called the routing table. The routing table needs to be configured in advance. It is not like our MAC address table, which can work without configuration. Once the routing table is configured, it will generate some routing entries internally. For example, in the future, if I find that you need to reach 2.0, then I find that the exit interface for 2.0, which interface does it go out from? It goes out from the G001 interface. Now, during this process, if I don't make any changes to the original MAC address or the destination MAC address when it is sent to switch 2, can switch 2 know the MAC address of AR1's G000? It cannot know because the 000 interface is not connected to our switch. So actually, if our router is forwarding across subnets here, it will change the original MAC address in the data, and the destination is to help the data find each other better. So here, the original MAC address will be the MAC address of A21's 001. And what is our destination MAC in this process? It needs to ask, as it knows it, is in the 2.0 subnet. And now it needs to find 2.1, so it will help you send an ARP packet. It asks, excuse me, what is your MAC address for 2.1? This is a broadcast packet, and once the switch receives it, it will copy and send it from all remaining interfaces. Only PC3 knows, oh, I am 2.1, you are asking me, and it will give a reply. Now, R1 will know, oh, so PC3's MAC address is this particular address. Then it will store it in its own ARP table. If we want to check the ARP table on a router, the command will be different. On our PC, it's ARPA, while on our router, it's display ARP. This is because the underlying systems they use are different. Now, during this process, we can see that it knows R1. And the MAC address table image of the remaining devices connected to us. Then in the future, based on this MAC address table image, the destination MAC address is encapsulated to our switch here. The switch checks its own MAC address table, and in this process, it finds, hey, you need to find this 3049. During this process, display mic address is now here at 3049. In this case, I haven't learned it yet, so it might have aged out. For example, here, if I use my PCE to access it again, because in this case, our MAC address table, if it automatically learns from receiving data, it also has an aging time. The aging time is 5 minutes. If I receive data within 5 minutes, I will refresh this 5-minute timer. If I don't receive data within 5 minutes, it will age out. Well, now, if we display the MAC address again, we will be able to see it. Okay, on port 002, I learned this 3049. In the future, I will send it out from this port number 2. And PC3 will be able to receive it. After receiving it, well, when we ping, we emphasize that I send to you and you need to reply for me to know that we can communicate. So PC3 will also encapsulate the original IP, destination IP, original MAC, TIT, and destination MAC. At this point, the original IP and destination IP will be reversed because now 2.1 needs to reply to 1.1 and the sender is 2.1. Upon receiving it, the future destination is 1.1. At this point, the original MAC address will be my 3049, and then I send it to whom? I send it to our AR1, right? AR1 here has a J001 port because this 001 is the interface. Its destination MAC address can be seen here, and its gateway is 2.254. It needs to send it to this destination through the gateway, so the gateway's address is written here. It is sent to our switch, and the switch checks its own ARP table, which has been written. To reach 2B28, it goes through G010 and sends out from this interface. At this point, the router will check its own routing table using display IP routing table. The routing table indicates that if we want to return to 1.0. Now, from here, it goes out through my 000 interface, and in this process, it will also change the source MAC address and destination MAC address. This is to facilitate the remaining switches to forward according to the original MAC. At this point in the process, the source MAC will be from whichever interface I go out, that is, from whichever interface I use. my address, so my 000 interface, and in the future, my destination MAC address will be the MAC address of our PCE. Now, in this process, I send it to the switch, and the switch will perform a lookup based on its MAC address table. Here, we can use the display MAC address command to view the learned MAC address table. Now, you can see that we need to find this 79D2 and send it out from our 0001 interface, and now PC1 can receive it. So, our entire data communication is actually based on this method. Here, PC1 uses the ARP table to encapsulate the destination MAC, Lotcha, and then the switch queries the relationship between the destination MAC and the interface to assist with forwarding. And our router queries the routing table to perform forwarding, checking which network segment the route is connected to on itself. In this process, it also needs to convert the original MAC address and the destination MAC address so that we can communicate normally in the future. This is why the three most important tables in our entire network communication are the ARP table, the MAC address table, and our routing table. The routing table contains our interfaces and our network segments and their corresponding relationships along with various protocols. If you are interested in networks in the future and want to learn more in-depth network content, or if you want to study Huawei certification technology or obtain Huawei certification question banks, you can send me a private message. I can also leave more comments below the video for technical exchanges.